All right, folks. Today is the scariest naming and easiest section in the book. Promise. Welcome to Calc 1, but more. So, first, today we're learning limits, derivatives, and integrals of vector valued functions. Vector valued function sounds scary. It's not. It is just a function that takes a number t and turns it into a vector, say v. You guys have dealt with these. They're really just how we make parametric curves. So what I'm referring to all day today is something like, that's a little hard to read, r of t, which is some vector valued function, right? So it's a function that's got an x coordinate that depends on t, a y coordinate that depends on t, a z coordinate that depends on t. We tend to do these in 3 dimensions, right? So this thing r takes the real numbers and turns them into a 3 dimensional real number, right? A 3 dimensional real number treated as a vector. So that's really what we're doing. This same process works if you replace this 3 with 17. Nothing changes here. Um, and you guys already know how to do this. This is all incredibly easy. The real like kick of this whole thing is something I'm not going to show you anyway. I'm just going to define it. So I'm going to say that the way I mean, like taking a limit as t tends to a of r of t, I'm just going to define what I mean by this. What I mean by this is take your brackets, take the limit t tending to a of x of t, put a comma, take the limit t tending to a of y of t, put a comma, take the limit t tending to a of z of t. Like, nothing new here, nothing surprising. And what this means is that you can just basically slap limits willy-nilly through vector valued functions. You already know how to do some stuff with vector valued functions. You already know how to, like, I don't know, add vectors together. You already know how to multiply by scalars. So I'm just going to make some more definitions. I'm going to be like, all right, look, so r prime of t, what I'd put in here, I'd normally go, well, let's see, there's a limit definition of a derivative, right? I'd do like the limit as like, I guess, h tends to 0. I'd do r of t plus h, then I'd subtract r of t, divide this whole thing through by h. Okay, let's tease this out. This might make sense, it might not. Do I know how to take limits? Well, I don't know. I don't know what this stuff in here is. And PS, this is me defining, right? So I'm using a what's called a walrus equals here. I'm saying, see the cute little walrus. This is me saying the way I'm defining this symbol is with this. This is how you guys normally define a derivative. So let's kind of tease ourselves into having this thing make some sense. So here I'm going to take some parts. So this piece here, right here, this guy's a vector. Right, categorically that's a vector. This guy here is a vector. So the operation between the two here is subtraction. Well, really, I'm going to think about that as adding -1 times a vector. That's scalar multiplication there. Adding is vector addition. I'm good with that. This whole top is a vector. Right? That's this whole top thing is a vector. Now the bottom thing's tough. That's a scalar, right? Because I'm adding it to t, it has to be a scalar. This divide by sign doesn't really make a lot of sense. So I'm going to have to scratch that a little bit. We're going to have to take that out of the bottom there, and we're just going to put it out front. So we're going to say it's actually 1 over h times this stuff. Let me rearrange my handwriting here just a little bit. Oops, that didn't go super well. All right, so my handwriting rearrangement I'm doing is I'm taking this thing that was on the top, scooting it over here. Oops, I lost a part of my t. I'm putting a 1 over h out here. I'm multiplying that. That's the same operation I wanted to do a minute ago. It's just that now I'm multiplying by 1 over h instead of dividing by h. Doesn't make any difference in the world. This thing here is a scalar. I've got a scalar times a vector. That means I'm doing scalar multiplication. Okay, all the operations here make sense. So there you go. What does that mean? Well, if I do this component-wise, I'm going to get, well, here, I'll do the first one. So if I do this component-wise, I've got here my r of t plus h, and the first component has x of t plus h. And then it's got y of t plus h and some other crap, right? And then here I'm subtracting. And here I've got x of t, and then I've got y of t and some other crap, right? That means that in this first coordinate, because I can distribute the scalar into all the coordinates, and because I can just distribute the limit, apparently, I'm going to have, because that's how I defined taking a limit here, right? I'm going to have the limit h tending to 0, and in this first component, I'm going to have x of t plus h minus x of t all over h. And now this is actually scalar subtraction, so dividing here actually does make sense. Then I'm going to have the same thing for y. I'm going to have the same thing for z. That's going to get me to a vector that's got an x prime of t in the first spot, a y prime of t in the second spot, and a z prime of t in the third spot. That's all there is here. Basically, that ddt thing, you can distribute it, right? Like this whole thought about differentiation, I could think of as ddt of r of t acts like scalar multiplication, right? I just think to myself, oh, right there, there's invisible scalar multiplication. And then I can just treat ddt like a scalar. All works out. And it's really just because we defined this way to take a limit. We said, look, the limit of a vector valued function is just the limits of the components. If any one of those limits collapses, then the whole thing collapses. That's fine. If one of the components isn't differentiable, then the function wasn't differentiable. No big deal. That's it. So I've got limits here. I got derivatives here. And let's do integrals real quick. So it shouldn't be a surprise that integrals work basically the same way derivatives do. You just do it piece by piece. So let's throw some notation at you. We're going to have some occasion to do indefinite integrals here. We're not going to have a lot of occasion to do definite integrals. So if we were doing a definite integral, we'd be going from integrating from a to b, say r of t dt, and we'd throw some sums at this. We'd throw a limit at those sums. We know that we can break things kind of component-wise. We can do vector addition. We know we can do that multiplying by delta x piece by piece, right? We can, that's kind of a scalar multiple, so we can throw that into each component. Then we know we can do the limit for each component. So we really should be able to pretty easily get away with the idea that we're going to integrate from a to b. We're going to have x of t dt here. Then in the y coordinate, we'll have our integral from a to b. That's a really trash integral, Joe. We'll have y of t dt there. In our third component, we'll have the integral from a to b. Again, we'll be integrating c of t dt. These are all one-dimensional integrals. This is just like any of these problems you're solving, or you're, instead of doing one Calc 1 problem, now you're doing 3 Calc 1 problems, but they're still Calc 1 problems, or maybe Calc 2 problems. They're not super duper hard. When we're doing indefinite integration, which is going to be really kind of a thing we actually do a little bit, we're going to just indefinite integrate in each piece. This is, you'll need to remember the plus c's. There will be a different plus c for each piece, but that's all there is. You're going to anti-differentiate x of t dt in the x coordinate. You're going to anti-differentiate y of t dt in the y component, and you're going to anti-differentiate z of t dt in the z component. Like, that's it. That's all there is. Easy peasy. I want you guys to spend a second see if you can think about the uses of this. We are going to use this a lot more in a couple of sections here. So see if you can figure out what that use is. Go through the homework, do these. They're just a bunch of Calc 1 problems. It's not super hard. If you get done with it quickly, jump ahead to the motion and space section. Work on that homework. It's the same stuff, but with application. So basically, it amounts to let's get right into kinematics. Let's do some kind of rocket sciencey stuff. It's pretty freaking rad. This section seems super dumb because it's just introducing the idea and practicing. The section on motion and space is where rubber really hits the road. Go explore it. It's cool. There's some neat pictures we could draw with Math 3D or GeoGebra or whatever. So I encourage you to go play with those. It's fun.